Right, this video we are looking at radicals, radical expressions. We'll simplify them. We'll do some operations with them. We'll look at other ways of expressing radicals, and then we'll use the idea of radicals to solve a right triangle with Pythagoras. Here's a few properties of radicals that we use throughout this video. The first two you've probably seen before. It's just where if you're taking, say you're taking the square root of 4 squared, the answer to that is just plain 4. In the book and in my labs, we often put an absolute value around that, just indicating that we're forcing that to be a positive number. So it's actually positive 4. But sometimes you might need to see the absolute value of that there. And then if you have a radical where the index is odd, so say like the cube root of 4 cubed, then the answer to that is just plain 4. And we don't have to worry about positives or negatives with this one, because with cube roots, taking the cube root of a negative number is allowed. Okay, the next rule, and the next two or three, the next two are ones that we use all the time. If I'm multiplying radicals that have a common index, I can rewrite that under one radical, and then I just have the product of those two numbers. So for example, if I'm taking the cube root of 6 times by the cube root of 9, I could say, well, that's the same thing as the cube root of 6 times 9, or cube root of 54. And I could simplify that probably, but that's the idea, that if I'm multiplying radicals with the same index, I can write it separate like this, or I can write them together. Similarly with dividing, if I have the radical of a quotient, I can split it up and just take the radical of the numerator and the radical of the denominator separately. Another rule that we use sometimes is one where you have an exponent on the inside there. And if you have an exponent on the inside there that's the same as writing the exponent outside. So for example, if I have, say, the square root of 5 to the third. So that's the same thing as the square root of 5 all cubed. Okay, so those two are the same. All right, so let's take a look at simplifying radicals. And when they have a radical, this cube root or square root symbol is just basically saying how many groups of, whatever this number is, groups of 3 things are there underneath the radical. And really the goal of it is to try and get things out of the radical. So say if you had a fraction, the goal of that to simplify it is to break things down so that here I could divide both top and bottom by 2. So I'm doing some kind of an operation to break it down. This and this mean the same thing. So I want to do the same thing with radicals where I want to break things down. And in breaking them down, what I'm looking for are groups of whatever that number is out front that are inside. And if I can find some, then I can bring those out of the radical and simplify it. So there's a few ways of looking at this one. I'll show you a couple ways with the first couple questions, and then I'll sort of default to the way I like to do it. So what I'm going to do is I'm going to break down the stuff, the radicand, into things where I'm trying to find groups of 3. So 27 is 9 times 3. So far there's not 3 things that are the same thing. X to the 12th, oh, I could do that one, because I could rewrite it as x cubed times x cubed times x cubed times another x cubed. So this is a group of 3, there's a group of 3, there's another group of 3, there's another group of 3. Now you're probably ahead of me with the 9, saying, well, 9 is the same thing as 3 times 3 times this other 3, and then I have all that other stuff that's back here. So if I'm doing the cube root of something, I'm looking for groups of 3. Well, there's a group of 3 right there, so I can take that out of the radical, and I bring one of those numbers out. Okay, so 3 in, 1 out. Here's 3 x's, I can bring 1 x out. Another 3 x's, bring 1 out. Another 3, bring 1 out. Another 3, bring 1 out. And then I write down what's left inside. Oh, in this case, there's nothing left inside, so I don't need to write this part there at all. And I would just write my answer as 3x to the 4th, because I had 4 groups of 3 that I could bring out. Is that making some sense? Why don't you try? Do the pause and play thing. Okay, so this time we're looking for groups of 4 things inside. So 4 things. Well, the A's would be easy because I can say there's A, 4th, and then an A. So here's my group of 4 A's. B's, I could do B, 4, B, another 4, that's 8, and 1 more. There. So I've got 2 groups of 4 B's that I could take out. But that number, I have to worry about that number. Let's try and divide it maybe by, I don't know, 8, 16. I don't know, you can do it on your calculator. Maybe I'll try 2 first. So 768 divided by 2, what's that? 384. Okay, so I'd have 2 times 384. Let me divide 384 by 2 again. So that'd be 192. Oh, this is getting better. And then divide it by 2. 2 times 2, that'll be 80. Oh, 2 into that. Oh, so I'd have a 2. And then 2 into 192 goes 9, 6. Okay, let's keep breaking down. 2 will go into 96 48 times. Now you may want to check to make sure, multiply all that stuff and see if it still gives me 768. You see where I'm going with this though? Okay, 68 is 8 times 6. So I have 2 times 2 times 2 times 2, and then 8 times 6. Let me just write these as 2 to the 4th because I'm going for 4 things, right? And then 8 is 2 times 2 times 2, and 6 is 2 times 3. There's another group of 4 2's. So I could really write that as 2 to the 4th times 2 to the 4th times 3. And you could check that and see if that's right. Okay, so now groups of 4 things in, I can bring 1 out. There's a group of 4 2's, bring a 2 out. There's a group of 4 2's, bring a 2 out. So these are gone. I brought an A out. I need to bring a B for this one, another B for that one. And so then write down what I have left inside there. It looks like there's a 3, an A, and a B. And on the outside, I probably would simplify that. 2 times 2 is 4. There's only one A. There's 2 B's, so I'll write it as B squared. 4th root of 3AB. All right, hopefully you're catching on to those. Okay, when you're multiplying radicals, you do sort of the same thing. So if I'm multiplying these, I could write this all, they're all square roots, and I'll just write things together. So 3 times 15 is 3 times 5. See how I'm breaking it down, factoring it. A to the 5 and another A, that would be 6 A's. And then B squared and B squared would be 4 B's. Now, since this is a square root, nothing indicated, so we assume it to be a 2. I'm looking for groups of 2 things inside. So 3 squared, there's 2. 5 doesn't have a buddy. A6 I could rewrite as A squared, A squared, A squared. There's 3 groups of A squareds. And B, B squared, B squared. There's a group, bring 1 out. Whoops. Here's a group, bring an A out. Bring another A out. Bring another A out. And it looks like I have to bring 2 B's out as well. And inside, I'd be left with just a 5. So in rewriting that, I'd call it 3A cubed, B squared, root 5. Now, if you can see faster ways to do that, yeah, go ahead and try them. Here's a cube root of 1. Let me try this one. I'm going to rewrite it as cube root of 64A to the 4th and cube root of 27B cubed. On the top, I know 4 times 4 times 4 is 64. So I can bring a 4 out because that's 3 4's. A, there's 4 A's there, so I can bring 1 out, and I'll be left with inside just plain 1A. See, I'm sort of taking some shortcuts there. Hopefully you can do this kind of thing in your head. If you can't, keep doing it like that. That'll work. On the bottom, the cube root of 27 I know is 3, and here there's 3 B's. I can bring 1 B out. So that would be my answer to that question. Here's some to try. Press pause and play. Okay, so fifth root of 8 is 2 times 2 times 2. 4 is 2 times 2. That's convenient. X3 and X4 would be X7. Y4 and Y1 would be Y5. So in simplifying this, I need 5 things in to bring 1 out. So it looks like there's 5 2's there. Let's bring a 2 out. Of here, I can bring 5 of those x's out, and it'll become 1 outside, and I'll be left with 2 x's inside. And the y's, I can bring all the y's out. There's one group of 5 y's, I can bring 1 out. And so all I'd be left with inside is an x squared. Done. This next one, probably a number of different ways you could do this one. You could break down the top and break down the bottom, but you could also do this and just write it over one thing, just with one radical, A, B. And then 16 goes into 128 8 times, and A into A squared just goes A. B to the 4th divided B would be B cubed. So there, now I don't have a fraction, but I'd still have to worry about the square root sign. 8 is 2 times 2 times 2, and A, and then I've got B squared and a B. So I can bring that group of 2's out. I can bring those 2 B's out, and then stuck inside I'd have a 2, an A, and a B. Okay, so there's those questions. Now you can also add and subtract radicals, and you can only do that if you have a common radical. So these both have a root 3, so I can just add their coefficients, the 2 and the 9. So this would be 11 root 3. The next one, oh, they're not common. But maybe I could use some tricks that I've used in the previous questions to help me out with this. Let me try. So 45 I know is the same as 9 times 5 minus 8. And root 80 I think is the same as 16 times 5. Okay, using one of those rules that said if you're taking the product, you can just rewrite each one of them individually. Do the same thing over here. And then the square root of 9 is 3. So I'll have 12 times 3. Notice not root 3, it's just 3. Root 5 minus 8. Square root of 16 is 4. So I put it in brackets and it'll multiply by the 8. And then I have the root 5. 12 threes is 36, root 5, minus 8 times 4 is 32, root 5. Now they're both root 5, so I can subtract their coefficients. So it'll be 4 root 5. Go ahead and try this one, and then press play. 32 is 16 times 2. 8 is 4 times 2. And 18 is 9 times 2. So root of 16 is 4. 4 times 2, this would be 8 root 2. Plus, square root of 4 is 2. 2 times 3 is 6 root 2. Square root of 9 is 3. 3 times 4 is 12. Now they're all root 2, so I can add or subtract them. 8 plus 6 is 14. 14 take away 12 would be 2 root 2. When multiplying radicals, you do it the same as you would multiplying any binomial. So I'm going to be multiplying the root 5 times root 15. Whoops. Root 5 times root 15, root 5 times minus 3, this times this times this. When you do it, use like you always do, worry about what your sign is, then what your number is, and finally what your letter is. So root 5 times root 15 would be the square root of 75. Root 5 times a minus 3 is a minus 3 root 5. 2 times root 15 would be a plus 2 root 15. And lastly, 2 times a minus 3 would be a minus 6. Now simplifying, I need to look for radicals that are the same. None of these are the same. Neither 6. 75, I think I can simplify. Let me do that over here. 75 is the same as 25 times 3, and the square root of 25 is 5. So I can replace root 75 with 5 root 3. Oh, but still that doesn't give me a radical that matches any of the other ones. So this is where I would leave that question. Try that one. So there's 2, so I need to write 2 of these out like this, and then FOIL. 1 times 1 is 1. 1 times root 3 would be a 1 root 3. Root 3 times 1 is another 1 root 3. You don't need to put those 1s out front. And then root 3 times root 3 is a square root of 9. Simplifying a bit, I have 1 plus 1 root 3 and another root 3 would be 2 root 3. And the square root of 9 comes out to plain 3. Now here I have some like terms. So 1 plus 3, I can write that as 4 plus 2 root 3. You can also divide radicals. And when you're dividing radicals, and I guess we divided some, but one of the rules with dividing radicals is you can't have a radical in the denominator. So like in both these examples, I've got radicals in the denominator. And so if you have a monomial, what you do is you multiply top and bottom by something where you can get a perfect square on the bottom. And those perfect squares are, you've probably seen them, 4, 9, 16, 25, etc. Now 11, you can't multiply 11 by anything, an integer in order to get these. So maybe I could just default by multiplying that one by root 11. Because I know that the square root of 11 times the square root of 11 is the square root of 121. And when you figure that out, it just comes out to an 11. And then what you do is you just deal with what happens on the top. So I have 3 root 2 times root 11. That'll be 3. 2 times 11 is 22. Root 22. So my answer will be 3 root 22 over 11. Okay, the next one, a little tougher because this one's a cube root. So cube root, I need to have 3 things the same to bring one out. So on the bottom, I just have 1, 7. Let me rewrite the question. So 3a to the 4th over 7b squared. So I'm going to multiply this by cube root of, I only have 1 7 here, and I know I need 3, so I'm going to multiply it by 2 more 7s. Then totally I'll have 3 7s. I can bring it out. I have 2 b's there already. I'm just going to multiply it by another b, because then I'll have 3 b's. I'll be able to bring it out of the radical. Now, if I do that on the bottom, I have to do the same thing on the top. So on the bottom, I'm going to have the cube root of 7 times 7 times 7, b squared, or b times b times b. And just finishing off that, 3 7s bring 1 out. 3 b's bring 1 out. Notice there's no radical now on the bottom. Now I just have to deal with the fallout on the top. So on the top, I'll just write it down here. 3 times 7 times 7, 49 times 3. What is that? 49 times 3, 27 to 147. So it'll be 147, and then a to the 4th b. Now the last thing you can do with this one is right there, there's 4 a's, and all I need are 3 to bring 1 out. So I'm going to bring an a out. So I'll bring an a out to the front. Then I'll have the cube root of 147, and there'll be 1a stuck there and a b all over 7b. I'd like to be able to cancel this b and this b, but one's inside a radical, one's out. Can't cancel. Try that one. So I've got cube root 16 over cube root 9. If I simplify the bottom a little bit, it's a cube root of 3 times 3. So in order to get rid of the radical on the bottom, I'm going to multiply top and bottom by just a cube root of 3, because then I'll have 3 3's on the bottom. If I do it on the bottom, I have to also do it on the top. So on the top, I'll have the cube root of 48. I'll write it as 16 times 3 over, now I've got 3 3's. I can just bring one out. Now I left the 16 times 3 on the top because I think I can simplify that some more. So 16 is the same thing as 2 times 2 times 2 times 2 times the 3 all over 3. You see the 3 2's right there? I can bring 1 2 out, and inside I'll be left with a 2 times 3, which is 6 over 3. Okay, so that's rationalizing if you have a monomial. You can also rationalize if you have a binomial like this one, where you have 2 terms. To do that one, you need to multiply top and bottom by the conjugate of this. You might have heard the word conjugate before. If you haven't heard it before, it basically just means multiply top and bottom by the same thing that you have on the bottom, except you change that sign. So if it's a positive, you change it to a minus. Notice that none of the other signs change, just that middle one. If you multiply on the bottom, you also have to multiply it on the top. Okay, so now let's multiply and see what happens here. So on the top, multiplying this would be a minus 4 root 35. This times this would be a positive 4 root 21. On the bottom, root 5 times root 5 would be the square root of 25, which is just 5. Root 5 times minus root 3 would be a minus root 15. Root 3 times root 5 would be a positive root 15. See what's going to happen there? And root 3 times a minus root 3 would be a minus root 9. So, on the top, minus 4 root 35 plus 4 root 21. On the bottom, these two will cancel. The square root of 9 is 3, so really I have 5 take away 3, which is 2. Last thing I could do with this one, and after all that work, I'm sort of done. But the last thing you could do is you could, on the top 2, you could factor out a 2. And you'd be left with minus 2 root 35 plus 2 root 21. Notice I just factored out of that number and that number. And then the 2's there are common, a factor of 1, so I can get rid of them. So my final answer would be minus 2 root 35 plus 2 root 21. Okay, there's one for you to practice. Try it, see how you do. Okay, so I'm going to multiply, I'm just going to get rid of that, multiply by a root 3 plus root 6 on the top and the bottom. So on the top, I'll have root 3 plus root 6 minus root 6, minus root 12 over, on the bottom, root 9 plus root 18 minus root 18 minus root 36. On the top, I have root 3, root 6 minus root 6, those cancel, interesting. Minus, now root 12 is the same thing as 4 times 3. So really I could write that as 2 root 3. Because this is root of 4 times 3, and the square root of 4 is 2. That's where I got that from. Square root of 9 is 3. These cancel. Square root of 36 is 6. Okay, on the top I have common radicands. So 1 root 3 minus 2 root 3 would be a minus 1 root 3. And on the bottom, 3 take away 6 is a negative 3. Seeing as how I have a negative on top and bottom, I would cancel both of those. So my final answer would just be root 3, over 3. Now, I can also write radicals as fractional exponents. So here I have, and you probably haven't seen fractional exponents much before, but you can rewrite those as a radical. And so the x goes underneath. Whatever the bottom number is, that becomes your index. And whatever this is becomes your exponent of x. So this next one, I would rewrite it like this. So there's a radical. 27 is a big thing. This goes as my index, and this number goes as my power. There. Now this one here, I could simplify that. Might as well do that while we're at it. So I have 27, and that's 27 to the fourth. So that means there's 4 27s, right? Times. And here's a group of 3 27, so I can bring 1 27 out. And then I have a 27 inside. Oh, now 27, couldn't I rewrite that one? Cube root. 27 is 3 times 3 times 3. So there's a group of 3. I could bring a 3 out too. So it'd be 27 times 3, which would just be equal to 81. Interesting. Now you can, if you want, just try that on your calculator. Do that. Go 27 to the 4/3. You might need to put 4/3 in brackets, and hopefully it'll come out to 81. There's one for you to try. I'll do it. First thing with this one is I would change it to a fraction or to a positive exponent. So 32 to the 4/5. And then be 1 over the 5th root of 32 to the 4th. Now, this is one where I'd use one of those rules where it's the 5th root of 32 all to the 4th. Because I know the 5th root of 32, try it on your calculator, comes out to 2. Because if you go 2 times 2 is 4, 8, 16, 32. So there's 5 2's in 32. So 5th root of 32 is just plain 2, and then I have 2 to the 4th. So that would be 2 to the 4th, I think, is 16. So your answer would be 1/16. Okay, last concept for this section is Pythagoras. You've probably done that before. Each of those letters have a specific spot where they go. If you have a right triangle, the side opposite to the right angle is always the hypotenuse or letter C. The other ones, here's angle A, so the side opposite of that is side A, and this was side opposite to B is B, side B. Okay, so if I have a question, say I've got, I'll do a nice easy one. Say B is 6 and A is 8, and I want to know what side C is. So I can just plug them into my formula. A is 8, so 8 squared plus B is 6, 6 squared equals C squared. 8 squared is 64, 6 squared is 36. And to solve for C, I'll add these to be 100. And then I can use a square root property that we've done before. We should put a plus or minus here, but in this case where I'm looking for the length of a side, I probably won't use the minus version. So I'm just going to say that C is positive 10. All right, it's a long video. We looked at radical rules, we looked at operations with radicals, found that there are lots of them. We saw that you can express radicals as a fractional exponent. And lastly, we just did a quick little example of using Pythagoras and seeing where square roots come out with that. Okay, try some homework questions, your video quiz, and as always, if you have questions, ask me.